Welcome. Today we'll be discussing section 2.4. Topics include periodicity, graph of a trig function, as well as examples. So for the periodicity of a function, we know that in order to qualify, there must exist some number p greater than 0 such that f of x plus p is equal to f of x. And that's for all x. In other words, I can take a part of the graph, and if I add p, so if I just kind of shift it over by p, I get an identical part of that same graph, and I can do this over and over and over again for as long as I'm within the domain of f. So to solve these sorts of questions, we want to find a base interval, and we want to have solutions in the form of x equals a base, so some answer within a range, plus my interval times n being an integer. Sine, cosine, secant, and cosecant both have a period of 2 pi, and we'll see this explicitly in a bit. Tangent and cotangent have a period of pi. So we're now going to draw the graph of these trig functions. So if I have a graph like this, and I'm going to start by plotting sine. So I'm going to have white be sine. Y equals sine of x. This will be my little key. All right. Well, let's first mark out, here's pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, and 3 pi. And then here we have negative pi over 2, and negative pi, negative 1, sorry, 1, and negative 1. All right, so sine of 0, we know is 0. Sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2 is negative 1. Sine of 2 pi is 0. And we get a graph that looks like this. Go back up to here and come down like that. We can also go in the negative direction, and it'll look something like this. And this continues forever. Now, properties of this graph include the domain is all reals. So I'm going to write this as this fancy looking R. This is the same as from negative infinity to infinity. My range is what y values can I obtain. I'm kind of trapped between 1 and negative 1. So I'm going to put a bracket, or bracket, negative 1, comma, 1. My y-intercepts, I have one of them, and that's at 0. And my x-intercepts, I have multiple of them, and that's when x equals 0. But I also have to include all the other ones. Since my period is 2 pi, let me put that in here. I can go, hey, 2 pi n, 2 pi. But that only covers half the solutions, because I'm covering here and this one, but I'm missing the solution at pi. Well, I can add those solutions in by simply just going from x equals pi n, and that will hit all the solutions now because we have 0, pi, 2 pi, 3 pi, so on and so forth. Absolute maximum, that is y equals 1, and that's obtained at, so I'm going to use a fancy looking A. Y equals 1, and then where's this at? That's at pi over 2 plus 2 pi n. Now, what's important is I'm using pi over 2 because I want to reference an angle within my first interval, my preferred interval, and we'll talk more on that later. Absolute minimum, when's that obtained? That's obtained here, and that is 3 pi over 2. So the absolute minimum is y equals -1 at 3 pi over 2 plus 2 pi n. Where is the graph increasing? Meaning that if I take any sort of step forward, so if I look here, if I travel to the right, I go up, that's increasing. If I travel to the right and I go down, that is decreasing. So I'm increasing from negative pi over 2, pi over 2. So I'm going to write this as negative pi over 2 to pi over 2. And that is certainly one interval, but I want all my intervals. We have a period of 2 pi, so I'm going to add 2 pi n plus 2 pi n. And now that covers, if I take this and I shift it up by 2 pi, I land right on its a mirror of it, or basically the same. Same kind of interval that's increasing. Decreasing, well, if it's not increasing, it's either constant or decreasing. We definitely don't have a constant function, so it's decreasing. And so we have from pi over 2 plus 2 pi n to 3 pi over 2 plus 2 pi n. Again, that interval is here, and we can subtract, and we'll find that same interval, or we can add 2 pi, and we'll hit that same interval, that same behavior. Is it even or odd? Odd is when we can rotate around the origin 180 degrees. Alternatively, if we have a function and we plug in negative x, if we get negative f of x, so if we have f of negative x equaling negative f of x, that is an odd function. And we have that with sine, as sine of negative x is equal to negative sine x. So yes, sine is odd. Preferred interval, well, we want to have a nice one, and what we deemed nice was from 0 to 2 pi. And I'm going to include 0 and exclude 2 pi. Why? Because now if I take this interval, I can repeat it for every other interval out there, and I have no overlap of any kind. Okay, so why do I want to know all this stuff? Well, we can get some properties. So we're going to have the function y equals sine of x, and we have if y is not in the interval -1, 1, then no solution. So in other words, if I have a point that's outside of this bounds, my function can never hit it. It's outside of the range. I can never hit that value. That is with the base function. Something to know, all these properties that we're listing here are with the base function. We'll cover how we can manipulate functions later on. But so for now, if I'm not within the range, there's no solution. If y equals 0, then x equals pi n are all the solutions. So in other words, where my x-intercepts are was pi n, so I'm just restating that here. Okay. If y equals 1, then we have x equals pi over 2 plus 2 pi n are all solutions. D, if y equals -1, then x equals 3 pi over 2 plus 2 pi n are all solutions. So what do I mean by these two statements? Well, the first one, we know that at pi over 2, we get 1, and we're simply just adding 2 pi to it. Or we could subtract 2 pi. That's what the n does. Okay, and then the next one, I'm working within my preferred interval, and I find one solution in there, and I say, okay, 3 pi over 2, that gets me -1, and now I'm going to add 2 pi or subtract 2 pi, and that gets me all the rest. Okay. So I want to add a few more, and that is if 0 is less than y less than 1, in other words, if y is positive, then the basic solutions are x1 equals pi plus x reference, and x2 equals pi minus x reference. Now what this x reference is that we're going to take whatever value of y, and we're going to have sine of x reference equals the absolute value of our y value, and our x reference is going to be within 0 to pi over 2 inclusive. So we're including 0, including pi over 2. We're going to do an example to show what I mean by this. And for f is if -1 is less than y, and is less than 0, then the basic solutions are x1 equals x reference and x2 equals pi minus x reference. So, so this is what we're going to use. What we're going to do is then say that x, so how like a solution would work, solutions would be in the form of x equals x1 plus 2 pi n, or x equals x2 plus 2 pi n. So it's an or statement and it would capture both of these periods. We'll explain this in a bit. So let's go through an example. Let's say sine of x is equal to square root 3/2. So we have to think, okay, what value gets us this? And I think there's an error in this statement. Let me fix it real quick. These bounds are reversed. -1, 0. This is 0, 0, 1. All right, I'll show you how I caught that error in just a second. So square root 3/2. That is about here. We get that when we have pi over 3. We can find that through our x, or through our unit circle. So our x reference is equal to pi over 3. So we have a positive y, and we found that our x1 will be equal to our x reference. So this equals x1. And then we can write down that x2 is equal to pi minus pi over 3, which equals 2 pi over 3. And if we look on our unit circle, we'll find that we'll get the same value of square root 3/2. But we can also see this on this graph, because if square root 3/2 is approximately here, and we go one more third over, we hit about the same spot again. And now each one of these solutions, since we're a periodic function of 2 pi, we're going to take each one of these references and add 2 pi to them. So I would say that x is equal to pi over 3 plus 2 pi n, or x is equal to 2 pi over 3 plus 2 pi n. And that is what my answer would be. This, because of this part covers the increasing portion where we hit square root 3/2. And then the second part of that answer hits the decreasing part where we hit our answer, and then every copy of it. Okay. So what does it look like if we have a negative? So let's do an example like that. So let's now have y be, or let's have sine of x equals -1/2. So to find our reference, we first want to try to find the sine of x reference equals 1/2. And we can memorize this or look at a unit circle and say, okay, that was obtained at pi over 6. So we're going to have x reference equals pi over 6. And to obtain our solutions, we're now going to take our reference and perform these operations. And we're going, or these operations, I should say, because y was negative. And we're going to have pi plus pi over 6 equals our x1. So that is 7 pi over 6. x2 is equal to pi minus pi over 6, which equals 5 pi over 6. And we're going to conduct the same thing of go x is equal to 7 pi over 6 plus 2 pi n, or x is equal to 5 pi over 6 plus 2 pi n. Now, the reference angle was found in our preferred interval, and then we just added 2 pi, subtracted 2 pi to each one of our answers. And this gives a blueprint on how to do that. I implore you, with the unit circle, we could have found these answers faster by going, hey, if I go negative pi over 6, I get my answer of negative 1/2. And then if I add 2 pi to that, I'm now here. And what's that spot? That is 5 pi over 6. Okay, well, if I'm here and that got me my answer, how do I get this one? All right, well, I can look at my unit circle and again obtain this and say, hey, that was obtained at pi over 6. Or, yeah, negative, sorry, we have negative pi over 6. Here we have 7 pi over 6. And 5 pi over 6 is here. So it's just after the top part of the unit circle. And that's how we could have obtained either of these. Well, regardless, the reference angle by using this method is able to obtain both. However, this is with the base formula. Later on, we're going to have a graph transformations and show how we can apply these with graph transformations. That's in a future video. So now we look at we'll look at the following. We'll look at sine. So let's first graph the sine function. If I start here, sine of 0 is 1. Sine of pi over 2 is 0. Sine of pi is -1. Or sorry, cosine of pi is -1. And so we're going to have the graph look something like this. And fill it out, like that going the other way. Okay. So this process repeats. So our domain is again all reals. Our range again will be from -1 to 1. Our y-intercept will be y equals 0, or sorry, y equals 1. And our x-intercepts, we have to work a little bit harder for them this time. Find the first one and say, okay, That's at pi over 2. And if I add pi, I get pi over 3 pi over 3 pi over 2. So I can rewrite this as pi over 2 times n. My max is again at y equals 1, but this time we have to find where we start. We started at 0, so we can just have at 2 pi n. For my minimum, we have y equals -1, and we find that first occurrence at pi. So we're going to put pi, we're going to add 2 pi n. For when we're increasing, we want to find the same sort of intervals. And when I look, we're increasing from pi to pi over 2. So let's write pi plus 2 pi n to 2 pi plus 2 pi n. Or decreasing, we can find that we're decreasing when we start at 0, so we can write 2 pi n. And we stop decreasing once we get to pi, so we're going to put pi plus 2 pi n. Even or odd? Well, cosine of negative alpha equals cosine of alpha, meaning it's an even function. It's mirrored across the y-axis. So cosine is even. And the period remains at 2 pi. And the preferred interval, it will be the same of 0 to 2 pi. Exclusive of the 2 pi. Symbolized by the parenthesis. So what use is this? Well, we're going to have a very similar statement structure, but now we're going to modify this to accommodate for cosine. So the first thing that we want to do is define our function as cosine of x. And for your check on learning this week, it'll be to write down these lists of properties, A, B, C, D, E, and F for cosine, y equals cosine of x. So if y is not within -1 to 1, that interval, then we have no solution. If y equals 0, then the solutions are x equals pi over 2 plus 2 pi n. Sorry, plus pi n. Because we hit the solutions here, and now we can add just a pi each time, and we'll hit another 0. If y equals 1, then that's the same as our maximum. So x equals 2 pi n. That hits every single maximum. Y equals -1. Well, we just have to choose the value in our preferred interval, which is pi, and we're going to add 2 pi n. So x must be pi plus 2 pi n. Okay. if we have y being negative, but it's greater than 0 or greater than -1, then what we have for our references are, we have x1 equals pi minus x reference, and x2 is equal to pi plus x reference. And if we're positive, but not 1, or less than 1, I should say, then we have x1 equals x reference, and x2 equals 2 pi minus x reference. And how do we get this reference? It's simply cosine of some angle is equal to the value of y that we're looking for, or the absolute value of it, and we're restricting our reference angle to be somewhere between 0 and pi over 2. So an example of this is cosine of x equals, let's do negative square root 3 over 2. So we first want to take the absolute value of this angle. So we want to find our reference angle. So cosine of x reference is equal to the absolute value of negative square root 3 over 2, which equals square root 3 over 2. And we're going to look at our unit circle and say, okay, what do we get? What do we get this? Well, this occurs when we have pi over 6. That's when our cosine of this angle is pi over 6. All right, so x reference equals pi over 6. So we're going to plug this into our facts here, and we say, okay, x1 must be pi minus pi over 6, which is 5 pi over 6, and x2 is equal to 7 pi over 6. And we might recognize these from before. Well, that's because this is the complement angle of sine of -1/2. So what we get is x is equal to 5 pi over 6 plus 2 pi n, or x is equal to 7 pi over 6 plus 2 pi n. And pictorially, we can look at 5 pi over 6 and say, hey, that's about here. 7 pi over 6, that's about here. That looks to be about negative square root 3 over 2. And if I take this one, I get half the solutions by adding pi 2 pi n. And then the other one, I get my other copy of all the solutions. So now, what about tangents? But before I do that, I'm going to again reiterate that writing all of this down from the left side of the board to the example to right here as the check on learning for this week, for this video. So let's look at tangent now. Tangents is sine over cosine. So we can find some properties of it right away. We know that it's 0 at 0. And we can see that when cosine gets to 0, it's going to go asymptotic, meaning it's going to go something like this. And similarly, every single time cosine hits 0, it's going to go like this. And since we have it being sine over cosine, we can see that it should be about 1 when sine and cosine are equal to. So it should be more like there. And it repeats every pi intervals. So we can reset this, and we can now see that this is a very different function from what we've seen before. First things first is the domain. The domain of this function is, and this function being y equals tangent of x, is not all reals, but we're going to have it be when x is not equal to pi over 2 plus pi n, meaning it can be anything but these values. And that's because we go asymptotic at those values. The range of it is all reals. Any value of y I can hit because how this stretches to positive infinity and negative infinity. What's my y-intercept? That's when y equals 0. My x-intercepts, I can find an x-intercept at 0, but also whenever I add pi, so that's when x equals pi n. My absolute maximum, absolute minimum, none. Increasing. So where is this function increasing? Well, it's whenever I'm moving up on the y values are getting higher as I move to the right. So I'm increasing everywhere except where I'm not defined. So I'm going to write that as parentheses negative pi over 2 plus pi n, comma, pi over 2 plus pi n, close parentheses, meaning that I'm not including the point that I'm listing out here. I'm not including negative pi over 2, but everything right up to it. And then I'm increasing for this interval, and I'm going to repeat it for all the other intervals. Where am I decreasing? Nowhere. Am I odd or even? Well, if I have tangent of negative alpha that is equal to negative tangent alpha, so tangent is odd. What's my period? Pi. And so now what's my preferred interval? I'm going to take this, I'm going to plug in 0 for n, so I'm going to have from open parentheses, so negative pi over 2, 2 pi over 2. That's kind of like the baseline. We like things to include the origin. So that is just showcasing this part of the graph. All right, how can we work with this function? What sort of rules can we find? Well, we're not as restricted as before, because before there were some values of y that we just couldn't hit. If we are greater than 1 or less than -1, we couldn't hit those. We don't have that case anymore. We also have a very steady sort of graph, and so when we do our repetition to get all values, it'll be much simpler. So we have our function y equals tangent of x. The first thing that we want to do is go, okay, what do we have? We're going to define tangent of x reference is equal to the absolute value of y. And we want our x reference to be within the interval 0 to 2 pi exclusive of the 2 pi inclusive of the 0. Okay. So with this notation, we can say that A, if y equals 0, then x is equal to pi n. B, if y is greater than 0, then x naught. I say x naught, I'm going to write x with a little 0. It's just saying my starting value. If you want to write x1, you're not wrong for doing that either. That's just going to equal my x reference. And C, if y is less than 0, then x naught equals my negative version of the x reference. In other words, if I'm positive and I'm between, and I'm some positive value of y, I'm going to hit it somewhere between 0 and pi over 2. If I'm negative, all I have to do is really count for the negative value of that, which a negative times negative is a positive, and I'm going to get the same reference angle, but I'm going to have the negative version of that reference angle because it's an odd function. So what does this leave us? This leaves us that all solutions, so D, all solutions in the form of x equals x naught plus pi n. So similarly, when I had the x equals 0, I could really think that I had like a 0 plus pi n and x not being 0, which then that just goes away. But here, basically, I have to find an angle, and then I just add pi n to it. And then I get every single one. And because we don't repeat like the sine wave, we can hit a value more than once beyond the period. With tangent, well, in every period, we hit every value once and only once. So it's really nice that way. Okay, so how can we do things with this, or what sort of solution can we do? Well, here's an example. Tangent x equals, and let's do -1. So I have to see, okay, my tangent of x reference is equal to absolute value of -1, which equals 1. Tangent of 1, what gets me that? Well, that's pi over 4. So x reference equals pi over 4. So that means x is equal to negative of my x reference since I was less than 0. So negative pi over 4 plus pi times n. And that's all the solutions that get me tangent is equal to -1. Okay. For the graph of the cotangent now, let's take a look at that. So for the cotangents, we have it being 1 over tangents, meaning it's going to look really, really similar. In fact, let me erase. Let me erase and redraw this for clarity. So if I look at, here's pi, 2 pi, negative pi, I'm gonna be asymptotic there. And my tangents look something like this. My cotangents I'm going to draw in blue. It's going to be 1 over tangent, so I'm going to be asymptotic whenever tangent is 0. And whenever tangent is infinite, I'm going to be 0. Okay, well here is a really high number that's positive. What's 1 divided by a really big, large positive number? It's going to be a really small positive number. So I'm going to look something like this. It looks kind of like tangent, but shifted and flipped. Okay. Well, what's my domain? My domain for cotangent is when x is not equal to pi n. And I can see that it's basically whenever tangent is equal to 0, that's where I'm not, as shown here. My range is again all reals. Y-intercept, there is no y-intercept because it's asymptotic at 0. There is no defined value at 0. My x-intercepts, that's going to be everywhere where tangent went asymptotic. So that was at pi over 2 plus n pi. So we're going to write pi over 2 plus pi n. And is there an absolute max? Nope. None and none. Okay. So increasing, decreasing, odd or even. Well, we can do our tests. So we're going to start with the increasing. Where is this function increasing? Nowhere. Okay, where is it decreasing? Everywhere that it's defined. So we can write that as what? From pi n to pi over 2 plus pi n. Oh, sorry, this is pi. Should just be pi. My bad. So we're gonna write pi here. I got my tangents confused. But we can see from here we're at pi to or 0 to here's 3 pi over 2. That shouldn't be that. Oh, that's why. Oh, that makes sense. Yeah, this is okay. I will. Yeah, pi over 2. That's where I want. That's what I want to do. Okay, yeah, no, I'm good. Is it odd or even? Cotangent is odd. My period is again pi. And my preferred interval is from 0 to pi exclusive. So where I messed up on this graph is these should be all over 2. So yeah, that's why that was looking really funky. You're probably screaming at me for that, but yes, this is supposed to be from pi over 2, and then that all works out. Yeah. That's what I get for moving quickly. All right. So now let's look at secants and tangents, or secant and cosecant. Now, you may have seen that I didn't go over an example with this or write rule set. It's because we can find them out through the other method of with the tangents, or its complementary function, and that would produce the same sort of set of equations or rules set, I should say. It's also not terribly important because generally speaking, we care about sine, cosine, tangent much more than we do of cotangent, cosecant, and secant. However, I still want to write down these graphs. And so let me redraw the graph here. And let's do secant. So now secant of x is 1 over cosine. So when we think back to the cosine function, it looked something like this, where this was 1, this was negative pi over 2, pi over 2, and this was pi. Now, for our secant, it's 1 over cosine. So 1 divided by 1 is 1. And then as we get to 0, 1 divided by a really small number is going to be really big. So it's going to look something like this. And we're going to have an asymptote. And now we have negative numbers. So it's going to look something like that. And then we're going to repeat here. So our repeating values isn't a pi interval, but a 2 pi interval. Our domain is going to be everything but when x is equal to pi over 2 plus pi n. Our range is going to be from negative infinity to negative 1 in union with 1 to infinity. Our y-intercept is going to be y equals 1. Our x-intercept is going to be none. Our absolute max is going to be none. But now we can say that we have a local max. And where's those local max? Well, if we look at just one of these, here we have no local max. Here we have a local max of negative 1. So y equals negative 1, where this occurs at what value of x? At pi in every 2 pi variant. So pi plus 2 pi n. Absolute minimum, none. But we have a local minimum. And that is y equals 1 at, and that occurs at every 2 pi n. Because we have a local minimum here, and then every 2 pi. Increasing. Well, for the ones that kind of look like a parabola going up, we're increasing over those intervals. That's from negative pi over 2 plus 2 pi n to pi over 2 plus 2 pi n. Decreasing from the interval of pi over 2 plus 2 pi n to 3 pi over 2 plus, oh, nope, I'm wrong. We're increasing from this point onwards to this point, excluding pi over 2. So we're increasing from 0 to pi over 2, and we're going to add the pi, 2 pi n, so 2 pi n to pi over 2 plus 2 pi n, exclusive, in union with pi over 2 plus 2 pi n. And where are we increasing to? To pi plus 2 pi n. And we're including that point, so it's a bracket. Decreasing is everywhere where we're not increasing that were defined. So that would be from pi plus 2 pi n to 3 pi over 2 plus 2 pi n in union with 3 pi over 2 plus 2 pi n to the point 2 pi. 2 pi plus 2 pi n. And including, so we're going to put a bracket there. Okay, is it even or odd? Is it mirrored about the y-axis? Yes, it is. Secant is even. Preferred interval, we have to include everything. So we want to include from negative pi over 2 to pi over 2 in union with pi over 2 to 3 pi over 2. And again, the parentheses means that we exclude the number listed. Okay. Now for the cosecant is going to be much of the same. So if we draw now sine, we can get a pretty accurate depiction of what's going on with cosecant. So there's my 1, -1, and now sine's going to look something like this. And so we're going to take 1 over this. So we're going to have our asymptotes here, here, here. Let's fill in these numbers. This is 3 pi over 2. This is 2 pi. And we're going to have another asymptote here at negative pi. And it's going to look much the same. Okay. And filling this out, we can see that the domain is now x when it's not equal to pi n. The range will remain the same. I'm just going to underline it. Our y-intercept is now none because we're asymptotic at the y-axis. For our x-intercept, it's again none. And same thing with absolute max, absolute min. But we have local max, local min. And that's going to be our local max will be y is equal to -1. Where does that occur? Well, that occurs at negative pi over 2, and then every 2 pi afterwards. So negative pi over 2 plus 2 pi n. Our local minimum, that occurs at 1 at pi over 2 plus every 2 pi n afterwards. So for increasing, we're going to start here and go to about here. And where is that interval? Well, that's at pi over 2, including pi over 2, plus 2 pi n, to the asymptote at pi, plus 2 pi n, in union with pi plus 2 pi n to where? 3 pi over 2 plus 2 pi n inclusive, so we put another bracket at the end. Decreasing is where everywhere else. So let's work with this interval from here to here. And we have it's decreasing from negative pi over 2 plus 2 pi n to 0 plus 2 pi n in union with 0 plus 2 pi n to pi over 2 plus 2 pi n inclusive. Is it even or odd? Well, it's 1 over sine, so it's an odd function. So cosecant is odd. What's the period? 2 pi. Preferred interval, we're going to go from 0 to pi. And then we're going to include the other part, which is from pi to 2 pi. That describes everything about the graph. Yeah. Thank you for watching and have a great day.